So today we're just going to look a bit further at redshift and what redshift means and how we interpret it. Bit of revision from yesterday, we found out about the German physicist Fraunhofer, who interpreted the light coming from the sun and realized that some of the colors were missing. The colors that are missing can be divided into what looks like a barcode and used to work out which elements are missing from the spectrum, meaning that the light absorbed by these gases shows which gases are present. If we look at the redshift uh, section of the notes, what we can tell is that when we look at the spectra from distant stars, we see similarly spaced black lines to those that we have in our sun. They appear to be shifted either towards the blue end or towards the red end. Here you can see it shifted towards the red and shifted towards the blue. This will let us figure out if the star is moving away or moving towards us. This is due to the Doppler effect. The same elements are generally present, but the light is shifted towards the blue end if it's moving away, and then if it's towards the red end if it's moving towards. This is just a little summary, really, of the diagram above. Light from distant stars is always shifted to the red end, which is our important part, showing us that all galaxies are moving further away, which is evidence for the Big Bang, that the universe is expanding. We have a formula for redshift. So redshift is just a physical quantity, and the formula for redshift Z is equal to the observed wavelength subtract the resting wavelength divided by the resting wavelength. So both of them are in meters. Let's highlight this whole section. Okay, it has no units. It's just a factor by how much the light has shifted, and as it's a factor, it doesn't have any units. So the observed wavelength is what you see on Earth. Take away the wavelength that we know is at rest, divided by the wavelength at rest. When it's moving away from us, the redshift is always a positive number. And when it is moving towards us, it is a negative. That's another way to determine, just by looking at the redshift number, what's happening. It can also be expressed using the formula Z equals the velocity over the star divided by the speed of light, where c is the speed of light and it is relative to the observer, who is typically on Earth. I have put some videos in the blog for you to sort of demonstrate these ideas a bit further than just obviously me filling in the page. We have a worked example here. So a spectral line for sodium usually appears at 589 meters. So that is its rest wavelength. Now the sodium star is observed and the spectral line is observed to be a wavelength of 598. So calculate the star if it's moving towards us or away. What is the redshift? What is the speed? So for part A, is the star moving towards or away? If the observed wavelength is greater than the rest wavelength, it is moving away. Okay, the Doppler effect, the wavelengths are being stretched out due to the fact that it is moving away as it produces the waves. B, what is the redshift for this star? So Z equals observed rest, take away rest, divided by the rest, 598, take away 589, over 589 gives us 0.015. Okay, now that's a positive number, and if you remember up here, if it's positive, it is moving away. So we can check that we've got it right just through that little method. Part C, what is the speed of the star relative to the observer? Well, we now know the redshift is equal to 0.015. That's a substitution. Okay. And we know the velocity of the star is what we're trying to figure out, and we already have the value for c. So we rearrange the formula, speed equals redshift times the speed of light. We are then able to calculate with our calculator the answer, the speed of the star, 4.58 times 10 to the 6 meters per second. So I will post this in with some supporting videos to the page, and then I'm going to list some questions for you to try based on these formulas. If you could really have a go at doing them and showing your working and putting it into the OneNote, that lets me actually pretend we're in the classroom by looking at your working, and I can see where you would make mistakes, if you're including units, if you're using the right sort of subscript in the formula, just as though we were in class. So it's important that you try these and put them in OneNote. Thanks.